Hello everyone, welcome to HealthGIS channel. In this video tutorial, we're going to practice several applications of epidemiology data analysis methods in R using a real-world foodborne outbreak investigation dataset. The outbreak occurred in October 1992, and we specifically are going to learn how to calculate the attack rate, risk ratio, and attributable risk for a cohort study, and also odds ratio for case control study, along with their confidence interval to assess whether the results are statistically significant or not. We will use EpiR package, a powerful tool for applied epidemiology analysis. Then we will learn how we can control for confounding variables using logistic regression model and calculate estimated odds ratio and their 95% confidence interval. So these methods are commonly used in outbreak investigation, surveillance, and risk assessment to evaluate potential sources of an outbreak. Let's get started. First, let's take a look at the CSV file. You can also download the data from the link in the description. The CSV dataset is a foodborne outbreak occurred in October 1992, and the data is for 77 individuals who attended a sport club buffet. And within 14 to 24 hours after the event, 51 people reported gastrointestinal symptoms, including diarrhea, nausea, vomiting, abdominal pain, and fever. The second column here, ill, indicates whether a person became ill, coded as 1. 1 means yes, they became ill, and coded as 2, which means that they didn't become ill. So the remaining columns correspond to the food items that were served at the event, also coded as 1 if they served the food, and coded as 2 if they didn't serve the food or if they didn't expose to the food item. So the included food items in the dataset are ham, beef, eggs, mushroom, pepper, pork pie, pasta, rice, and so on. So also all of these variables have been coded as 1 if the person ate the item, which means the person exposed, and 2 if the person was not exposed to the item. So now let's go ahead and load the data into R. So first off, let's load the data. So load the data. So read.csv and file.choose and header equals to true. And I'm going to store this in an object called food.data. So when you run this line of code, it asks me where's the data, and the data is foodborne outbreak, that you can also download it from the description and open. So here, if you open up the data, so here you can see we have the CSV file have been successfully loaded, right? So the next thing that I'm going to do is I'm going to look at the summary of the food data. And so as you can see, there are some 9 values in dataset which are missing values that have been coded as 9 throughout this dataset. So we can replace it with NA, like what we did in the previous lab, by subsetting, or we can address the missing values during the importing data process. So here, if you just add one argument, that na.string, so I'm gonna set this to 9, and then again reload the data, run and load the data. Now if you take a summary, you can see that we don't have the value of the 9, and all of them have been replaced with the value of NA. So NA.strings tells our which values in your dataset should be treated as missing value. We can go ahead and attach the data. So I'm going to attach the food data, which makes it easier to access each variable instead of using $sign food data $sign and then ham, food data $sign and then ill. So if I attach it, I don't need to use $sign. So click run. I'm going to visualize the data. So data visualization. So as you saw, all of the variables were categorical, right? And the plot that we often use for a categorical variable is bar plot. So I would like to use ggplot package to create bar plot for just illness and then compare it with another categorical variable like ham. So let's create a simple bar plot for illness. So load the package ggplot to run. We need to start with the keyword ggplot and then open close the parentheses. The first argument in ggplot is to specify your data set. So your data is going to be food data. So we also need to specify the aesthetic, which shows that which variables goes to the x-axis and which variables goes to the y. So we don't need to specify for y variable because it automatically counts the number of observation in each category. So here I am going to set the AES, aesthetic, and then I'm going to say that X is ill. So here make sure that you write it ILL, so it's ILL. So that's the aesthetic, and using this, the levels for the variables ill, which were 1 or 2, goes on the x-axis, right? So now we need to tell what type of graph should be created. Okay, so put a plus sign here. I'm gonna say that, so what kind of graph we're gonna create? We're gonna create a bar plot, and ggplot, the geometry for the bar plot is geom bar. So geom bar, and that's it. So if you run this line of code, what happens is that it created a bar plot for the ill, and the levels which are 1 or 2 are on the x-axis, right? So as you can see, most participants developed the illness, like over 50 participants developed the illness. So you can also confirm the exact count with table. So I can have a contingency table for example, ILL, ill. So I can see that for value of 1, we have 51 observation, we were 51 participants. And for the value of 2, which didn't have the illness, we have 26 participants. I also would like to compare it with another categorical variable. Okay, so let me copy this. So what I'm going to do is that among the people who got the disease, among the ill, how many had ham and how many didn't have ham, right? And among the people who didn't have illness, like 2 here, so I would like to see how many of them had ham and how many didn't have ham. So we have to modify this code so that it colors the bars with ham. So ham is going to be your grouping variable, but make sure that the grouping variable is actually a categorical variable or a factor. What we have to do here is that I have to fill it, so FILL, with the variable ham, but here you have to make sure that it is factor. Okay, so if you look at the, for example, str of the food data, so I don't think that this is, all of them are integer. So I can here easily convert this to factor, and so now this is a factor variable, so I have to close this. Okay, and then geom bar, so everything looks good. And let's run this line of code. So as you can see here, among the people who had the disease, like 1, so most of them were exposed, most of them had ham, right? So another thing that you can do is that you can make this bar plot side by side instead of stacked. You can set the position to dodge instead of geom bar. So here if I type position and I set this to dodge, so what happens is that instead of stacked, it's going to be side by side bar plot, and then run. So what happens is that here we can see among the people who got the disease, most of them had ham, and also among the people who didn't have the disease, most of them had ham, were exposed to ham. But look at the proportion, here is much higher than here, right? So I can also confirm this with the exact count with the contingency table, right? So for the contingency table, it's better to have the exposure first and then the outcome second. So exposure is ham and outcome is ill. So if I click run, So among the people who had the illness, how many of them had ham? 46. So also if you look at here, you can see it is almost over 45, 46. And among the people who had disease and didn't have ham, so here it's going to be 5. As you can see, it's exactly 5. Among the people who didn't have the disease, here, so 17 had ham, and among the people who didn't have the disease and didn't have ham, where the number was 9. Okay, so now let's move on to the EpiR part. So EpiR. So we're going to do some calculate some statistics that help us to determine which food item were most likely associated with the illness. So we're going to do this only for ham, but it is similar for all of the other food items. So you need to install the package EpiR. So, but I already have done that. So if you already have this package, you don't need to install it. But if otherwise, you have to install it, the package EpiR, and then load the package using library EpiR. So I'm then click run. So the very first important point for using the EpiR package is how you order the variables. We will use table functions that you just saw, but the first variable is always must be exposure, and the second variable must always be your outcome. And moreover, for the exposure, the order is important. The order is exposed and not exposed, and for outcome, the order is disease or cases, and then no disease or controls. Okay, so if I type again, and then the first one is your exposure, the second one is your illness, and also for the ham, so the first one is 1 means exposed, 2 means not exposed, 1 means disease, and 2 means not disease, right? So if I look at the data, it is the order is correct. So as you can see here, exposed are in the rows and outcome are in the column, right? And also exposed yes or no, or exposed yes or no, and outcome yes or no, or disease no disease. The format that is required for EpiR is correct, but if it's not in this format, you need to reorder that we will see in the next videos, how we can reorder the data in the format required for the EpiR. So the main function that we will use for EpiR is epi 2 by 2, 2 by 2. So, and the first argument is your contingency table in the order that we just discussed. Okay, so it's going to be table. So let me save this in table 1. Okay, and then epi table. So the first argument is going to be your table 1. And also you need to specify the method. So the method, what kind of, for example, is this a cohort study? Is it a case control study? So I'm going to use, let's say this is a cohort study. So it's going to be within the quotations. It has to be, the method has to be inside the quotation. So cohort dot count. So that's the method that we will use. And also the confidence level, conf.level, I'm going to find a confidence level at 95%. And then run. So what happens, it calculated a variety of statistics for us. Exposed group is the people who actually had the ham. So 46 of them, they got the disease, and 17 didn't have the disease. And how many were exposed in total? 63. So the attack rate is going to be 46 divided by 63, which is 0.73, but it calculates that the outcome is per 100 population. Also here we can see that the outcome is per 100 population unit. Okay, so 73% among the people who were exposed. And also it gives us the confidence level. So we are 95% confidence. The attack rate for among the exposed people is between 60% to 83%. And also attack rate among the unexposed people. So among the people who didn't have ham, how many of them have the disease? So 5 out of 14 people, so which gives us the 35%. So this suggests that attack rate is higher or more than double among those who exposed to the ham. So the next thing is risk ratio. So risk ratio is actually the risk among exposed divided by risk among not exposed. So which is actually 73% here divided by 35%, which is over 2. So the relative risk or risk ratio is 2.04, and we are 95% confident that the relative risk or risk ratio is between 1 and 4.19. So which means that people who ate ham or exposed were almost 2 times more likely to develop illness than those who didn't have ham. A 95% confidence interval is borderline statistically significant. So the next important statistic is attributable risk, or actually it is risk difference, which means that risk in exposed minus risk in unexposed, which means that 73% minus 35%, which if you do the calculation is almost going to be 37%, or 37 per 100 people. So which means that 37.3 more people out of 100 became ill because they had ham compared to those who didn't have ham. So this value shows the excess risk due to the exposure, due to the ham consumption that could theoretically have been prevented if the exposed group had the same risk as the unexposed group. Now let's say this was a case control study and we want to calculate the odds ratio, odds of exposure among cases divided by odds of exposure among controls. So the first thing that we have to do, we have to, instead of cohort.count, I'm gonna type case.control and then run. So here it gives us the exposure odds ratio. So how we can calculate the exposure odds ratio in this format? If you multiply 46 times 9 divided by 17 times 5. So let's see what we get. 46 times 9 divided by 17 times 5. So which gives us the value of 4.87, which is this value, 4.87, that's the exposure odds ratio. So the interpretation is that the odds of exposure, the odds of having ham among people who became ill was 4.87 times higher than among people who didn't become ill, among the control people. And the 95% confidence interval here also doesn't include 1, so it indicates that the association is statistically significant. So we can repeat these steps for all other food items to see which one is significant. If you notice, EpiR also automatically computed chi-square test here and also Fisher exact test. And as you can see, both of them, the probability is less than 0.05 here and also probability is less than 0.05. So both of them were, both of these categorical variables were significantly associated with each other. We are related. But the question here is that why instead of chi-square it used the Yates corrected chi-square, because the expected values are not that high. And also our study sample is only 77 observations, so the study sample is not that large, it's not over 100. So instead of just using the Pearson chi-square, it used the corrected version of the chi-square. And if you want to check that, you can also look at the chi-square test for table 1. And that's the value, p-value is here exactly. And also if you want to see the expected value, for example, I'm gonna save this in the object res, and then for example res, and then find the expected value. So you can see there should be some values, expected counts less than 5. So that's why instead of using the chi-square, it used the Pearson chi-square, is used the corrected version of the Yates corrected version of the chi-square. So let's detach the data and then load the data again for the next step. The reason was that I changed the format for some variables to factor, but for the logistic regression, I don't want to do that. All right, so now let's move on to the logistic regression. So when we looked at each food item individually using 2x2 tables, we identified associations between a food item and illness. But those associations could be confounded by other exposures. For example, maybe people who ate eggs also tended to eat pasta. So if pasta is the real culprit, eggs might appear risky just because they are often eaten together. So logistic regression helps us to adjust for multiple exposures at once. That means we can estimate the effect of each food while holding the others constant. And this helps us to find the true sources of illness. So logistic regression allows us to estimate this odds ratio, odds of becoming ill, adjusted for multiple foods at once, and identify the strongest predictors of illness. So let's load the data again. So I am going to load the data again. The reason was that that I changed the format here to factors. So I'm going to load the data again. Summary, and everything is integer. Those were either 1 or 2 or not available, but 1 means yes and 2 means no. But we need to recode these values to binary values of 1 or 0. 1 means yes and 0 means no. So we can use a trick that 2 minus all of these values. So what happens? 2 minus 1, 1. 2 minus 1, 1. And for the values are 2, 2 minus 2 is going to be 0. So what happens is that the values that are 1 will stay 1, which means that they were exposed or yes. And the values that are 2 is going to be 0. So not exposed values or no disease values is going to be 0. And exposed values or disease values is going to stay 1, which is great. So what I'm going to do here is I'm going to say that data. So, but here, what is the problem here? The problem is that I can't do that, for example, for the first column. So I'm going to select all columns from column 2 to last column, but all rows. So it's going to be for this data set, it's going to be all rows, and from column 2 to column 19. And then I'm going to store it in another data frame. So I'm going to, again, call this food.data. So in order to not confuse it with food data, I'm going to use the uppercase for F and D, and then run. So let's see what happens. So all of the values that were 1 now stays 1. All of the values that were 2 now they are 0. So now we can fit a logistic regression model. So we're going to use just a few items, for example, eggs, mushroom, pepper, pasta, rice, lettuce, coleslaw, and chocolate. Okay, so I am going to run a logistic regression model. So we use GLM function, GLM, which fits a generalized linear model. And the outcome is going to be ill. And then you have to use tilde, and then you have to use tilde and then other food items. So we're going to use multiple food items that are eggs, mushroom, pepper, pasta, rice, lettuce, coleslaw, and chocolate. So you have to separate them with plus sign. So we are saying that we're going to model the probability of illness as a function of multiple food items, eggs, mushroom, pepper, pasta, and so on. So now we have to specify the family, and the family is going to be binomial logistic regression. So I will put this logit as the default link function for the binary outcome. So it's going to be logit. And the last thing is that we need to specify the data. So we're telling R to use food.data, right? So the data here is going to be food data. And then I'm going to save this in a object, for example, logistic .foods. Has to be this eggs, and then run. Okay, so logistic function. So now if I take a summary of the logistic.food. So as you can see here, the summary identifies significant and not significant predictors. We're going to remove non-significant predictors step by step using backward elimination. So this stepwise reduction continues until we have all variables significant in the model. So let's begin with the least significant variable. So if you look at these variables, which one is the least significant? Definitely chocolate is the least significant variable, right? So I am going to, the next step, remove chocolate, right? So here I'm going to remove chocolate, and then run the model. So let's look at the results and also the summary. So now, as you can see, so we have removed the chocolate from the predictors. So which one is the least significant variable here? Definitely is gonna be this one, which is rice. So I'm gonna remove rice. I am going to remove rice and then run, and then run here. So which one is the least significant variable? So definitely it's going to be coleslaw, right? So now I'm going to remove coleslaw. So if I remove coleslaw here and then run and run, so which one is the least significant variables? Now pepper is the least significant variable, right? Run, run. So the last item is mushroom. So I'm going to remove mushroom and then run and run. All of the variables are significant. So the final model that we have is contains eggs, pasta, and lettuce. All of them are significant at 95% confidence level. So let's call this, for example, model, and also summary of the model. Okay. So the next thing that I'm going to do, the next thing is that let's look at the coefficients of the model. So if you type coefficient, coef of the model, so these are the coefficients of the models, and also we modeled the log odds of becoming ill in the logistic regression. Okay, so it's not the actual odds ratio, it's a log of the odds ratio. So what we have to do, we have to exponentiate the coefficients to get the odds ratio. So in order to find the odds ratio, I have to, so odds ratio is going to be exp exponentiate of the coefficient of the models. So if these are the coefficients of the model, if I exponentiate the coefficient of the model, I'm gonna get the odds ratio. So when you click run, and also if you look at the OR, so these are the odds ratio for eggs, for pasta, and lettuce, right? So similarly, we have to find the confidence interval of the model. So conf interval of the model, and also we need to exponentiate that one as well. So exp of the confidence interval of the models, which gives us the CI, confidence interval. And when you run this, so it is, so CI is this value. So all right, so we have the lower level and also we have the upper level confidence interval, right? So the last thing is that we just need to cbind odds ratio and CI. So if I type cbind OR and also confidence interval, so this is going to be your final result, final model. So when you run this, so and then if you look at the final results, so you have the eggs, pasta, and lettuce. These are the odds ratio, and you have the lower level and the upper level. As you can see, none of them crosses 1, so all of them are significantly associated with the illness.